Good morning, colleagues. My name is Yegor Nomakonov. I am a PhD student from St. Petersburg University and JetBrains Research. And today I will present the project we have made with Oli Lachov, Yonos Oberhauser, Anton Podkopayev, and Victor Vafiadis. In our project, we investigate what is the termination conditions for concurrent programs, given that the execution of these programs doesn't follow the intuitive concurrency semantics. And one important class of such programs are mutual exclusion algorithms. Suppose we need to restrict the access to the critical section for two threads. In order to do this, each of them executes locking before entering the section and unlocking after exiting it. A natural condition for such algorithms is that every client will eventually enter the critical section, which in turn is guaranteed by the termination of the lock procedure. But as it turns out, this is not trivial. Indeed, as Oberhauser et al. Observe, multiple existing lock implementations can hang being executed on real CPUs. Now let's see how a particular lock implementation can demonstrate non-terminating behavior. This is one of the simplest implementations of mutual exclusion, namely a Spinlock. The status of the critical section is represented by the shared variable L, where the value 1 means that the section is currently occupied, and the value 0 means that the section is free. Each thread that wants to enter the critical section tries to atomically change the value of L from 0 to 1. If the change succeeds, the thread proceeds, otherwise it tries again. After executing the critical section, a thread simply writes 0 to L, which allows other threads to enter the section. And for an intuitive interleaving concurrency semantics, it is not hard to see that both threads will eventually enter the critical section. The interleaving semantics states that the execution of the concurrent program can be represented as execution of single thread instructions interleaved with each other. The only requirement we need is that every active thread is eventually scheduled for the execution. This requirement is also known as thread fairness. Let's see how our program operates under such semantics. The scheduler picks one of the threads, suppose it's the first one, which executes its instructions until concurrent swap, and then enters the critical section. Let's briefly describe how we represent the program execution. When we execute a program instruction, we write down a memory access event that has just occurred. For a repeat instruction, there is no memory access event. In turn, since successful concurrent swap execution involves both reading from and writing to the memory, we write down an update event, which accounts for the memory address being accessed, as well as both read and write values. Now let's get back to the execution. At some point, a context switch may occur, which will cause the second thread to repeatedly try and fail its concurrent swap instruction. Note that the failing concurrent swap generates only a read event. But since the scheduler is fair, eventually the first thread will be selected again, and so it will write 0 to L. After that, the second thread will enter the critical section and terminate as well. To summarize, we required that every thread is eventually scheduled, and from that it followed that the second thread will eventually see the last write from this first thread. But this whole reasoning relies heavily on the interleaving semantics, also known as sequential consistency. Meanwhile, a realistic concurrent semantics, used for a hardware architecture or a programming language, should take into account possible optimizations that could be performed during the execution. These optimizations, when performed in a concurrent setting, may lead to behaviors that are not allowed under sequential consistency. More possible behaviors imply weaker guarantees for program execution, and this is why the semantics, or memory models, are called weak. Now let's see how a program can be executed under one of such models, namely x86 TSO. This architecture uses thread local store buffers. Each write operation first goes to a thread local buffer and is only propagated to main memory at some later point. While a write is still in the buffer, other threads reading from the same location will access only main memory and observe an obsolete value. Let's see how it affects the previous reasoning. The first thread enters the critical section. In order to keep the compare and swap instruction atomic, its execution bypasses the store buffer and operates directly on the main memory. Then a second thread tries to enter the critical section and fails. Eventually the first thread exits the critical section, but now, contrary to the concurrent swap, a regular write instruction puts its result into the store buffer first, where it can get stuck. Meanwhile, the second thread tries to enter the critical section, but observes the stale value fl and blocks, thinking that the thread 1 is still in the critical section. As you can see, under weak memory models, thread fairness alone is not sufficient to guarantee the termination. We also need to require that each buffered write is eventually propagated to the main memory. With this condition, the second thread will eventually read the latest write of 0 and proceed, similarly operating with its buffer and propagating its content at some point. This additional requirement for the buffered writes eventually propagating to memory resembles the one for the threads eventually being scheduled. That's why we call this condition memory fairness, similar to thread fairness. We have just seen how to formalize memory fairness for an operational model. We analyze the operational semantics, find the possible cause of unbounded delays, and require them to be bounded, which can be expressed in some sort of propagation. Note that the notion of propagation is not uniform and depends on the concrete model. As we just saw, for x86 we require that store buffers are eventually flushed. For sequential consistency, it turned out that we don't need additional requirements at all. For other models, there are other requirements, which we discuss in the paper. However, this whole approach only applies to operational memory models, where the execution of a program corresponds to a sequence of abstract machine states and still relies on the notion of interleaving. But many modern memory models are defined in another way, namely declaratively. Now let's see what is a declarative memory model definition. Simply speaking, the execution of program is represented as a graph. Its nodes correspond to memory access events performed by the program. This set of events is built one thread at a time. To analyze our non-terminating example, we build a graph where the number of events is finite for the first thread and is infinite for the second thread. Events from the same thread are ordered by the program order relation, whereas events from different threads are generally unordered. As we see, the graph consists of subgraphs corresponding to each thread, and these subgraphs are built independently of each other. That independence also means that we're free to pick an arbitrary read value when placing a new read event. But in order for our full graph to make sense, we need to justify all read events by relating them to some write. We can represent it with reads from edges that relate a given read event to an event that writes the same value to the same location. Note that we also introduce an auxiliary initializing event which writes 0. There are other relations as well. For example, most memory models also account for so-called modification order, which, simply speaking, represents that one write is being overwritten by another. For example, the non-initial write overrides the initial one. And the memory model itself is defined as a predicate on such graphs. That is, if an execution graph satisfies this predicate, then the memory model allows the execution corresponding to that graph. For example, one of the requirements of TSO is the absence of cycles made of program order, reads from, and modification order edges. But this is not enough to guarantee that the program terminates. Indeed, in our graph, there are no such cycles, so the corresponding unfair behavior is allowed. So we need to somehow extend the definition to prohibit this unfair behavior and ensure fairness. To do that, let's observe that an execution graph only contains memory access events and doesn't contain propagation events. That is, to ensure fairness, we need to find a declarative counterpart for them. Let's analyze how an unfair execution graph looks like. If the busy wait loop in the second thread never terminates, it produces an infinite number of read events, and each of them observes the value 1. Therefore, each of them reads from the update event from the first thread. Note that we omit the program order labels here for brevity. We can interpret the graph in this way. Each of these reads is performed before the final write of 0, because it observes the value written by a prior write in the modification order. In other words, each of these events reads before the last write in the first thread. It is expressed by the composite relation called reads before, which connects reversed reads from edges and modification order edges. This definition also excludes identity relation to correctly represent the semantics of read modify writes. Note that in the case of an unfair execution, the last write of 0 has an infinite prefix of reads before relation. That is, simply speaking, For the last right of 0, there are an infinite number of incoming reads before edges. That is, to ensure fairness, we need to require that this relation has a finite prefix. And now, with that condition, the demonstrated behavior will be prohibited, as we wanted to. A condition we have just described is not exactly a declarative counterpart for eventual propagation yet. Actually, there are similar examples that demonstrate that we also need to require the finiteness of the modification order prefix as well. So, as a result, we come up with the memory fairness definition expressed as a conjunction of two prefix finiteness conditions. And for the resulting fairness definition, we show that an operational definition of TSO, extended with eventual propagation requirement, is equivalent to its declarative definition extended with the fairness condition. Actually, the resulting declarative fairness definition turns out to be uniform. That is, we consider a number of other memory models, such as sequential consistency, reservoir, and strong coherence, where the last two are simplifications of the C++ memory model. These models have equivalent operational and declarative definitions for finite executions. And for each of these models, we show that adding our memory fairness requirement to their declarative definition yields an equivalent model as their operational model extended with a suitable ad hoc memory fairness requirement. And these results are formalized in COH. Moreover, the correspondence between the operational and declarative semantics yields a practical way to prove termination of concurrent programs. We show that if in a program with a bounded number of writes, a busy wait loop doesn't terminate, then it contains an iteration whose reads observes the latest write in terms of modification order. By arguing contrapositively, it gives us a direct way to establish termination of a program with busy wait loops. That is, the program terminates if its loops exit when reading from the maximal write. Pointing to our example, the second thread will eventually observe the value 0, which will cause the busy wait loop to terminate, which in turn contradicts the assumption of the infinite execution. In the paper and the code development, we also use this observation to prove the termination of the MCS log and the progress of the ticket log. Regarding the future work, we have been applying our uniform definition to other models. For the language level models, we've been working on supporting the RC11 model, which fixes some issues of the original C++ memory model. For that model, we have shown in the paper that the program transformations and compilation to TSO remain valid after requiring fairness. On the hardware side, we aim to support ARMv8 and PowerPC models. The complications here arise for a few reasons, one of which is that these models provide more complicated types of memory accesses. The other reason is that these models allow further kinds of unfair behavior, which we discuss more in the paper. Technically speaking, these behaviors arise because cycles made of program order and return edges are no longer prohibited, in contrast to so-called porf-acyclic models, which we consider in the paper. In summary, we show how to employ the memory fairness requirement in termination proofs for concurrent programs. Our paper provides multiple operational fairness definitions as well as a uniform declarative one, which applies to any porf-acyclic model. These definitions are proved to be equivalent for major memory models definitions, and we show how to use the uniform fairness definition for the verification of various log implementations. The key results are verified in COH. And that concludes my talk. Thank you for your attention.